Hi, I'm Paul. We're doing Leetcode Must Know interview questions, and today's challenge is minimum, genetic, mutation, rating, medium. Let me see the topics here. What do we have for topics? Breadth first search. Yeah. Okay, so yeah, it's a breadth first search. Hash table. Probably a hash table. Probably a hash set is what we want, but okay. So let's say a gene string can be represented by an 8-character long string with choices from the characters A, C, G, and T. Suppose we need to investigate a mutation from a gene string. Start gene to a gene string, end gene, where one mutation is defined as one single character changing in the gene, the gene string. For example, this first string to the second string is one mutation because one letter changed. The last letter changed from a T to an A. All right, there's also a gene bank. Bank. Let me move this over so we can see the method signature. What do we get in? We get the start gene, we get the end gene, and we get a string array called bank, which contains also gene strings. Okay, there's also a gene bank that records all the valid gene mutations. A gene must be in bank to make it a valid gene string. Given the two gene strings, start gene and end gene, and the gene bank, return the minimum number of mutations needed to mutate from start gene to end gene. If there is no such mutation, return -1. Note that the starting point is assumed to be valid, so it might not be included in the bank. All right, any constraints of interest? Whoa, what just happened? Okay, bank length from 0 to 10. All right. Start length, start gene. Okay, everything is 8 characters long and only contains A, C, G, and T. Okay. I've seen different ways to do this. I mean, I guess it's breadth first search any way that you do it, but let's say, if I want to like write the whole thing out, but let's say that let's use example 2. We have this A, C, G, C, C, G, G, T, T. All right, and we want to get it to this A, C, G, G, T, A. All right. Mutating one gene at a time. Okay, well, breadth first search, we'll use a queue. We'll put the start gene in the queue, and one way to do this is you can take the start gene and you can go through the bank and you can see one letter at a time, can I change this into a valid mutation? So let's say we go to that first one, AAC, right here, the first one. AACCGGTA. And you would do it one letter at a time. You would change like the first A in this to one of the other letters, like C. What if I change it to a C? No, that doesn't work. What if I change it to a G? That doesn't work. What if I change it to a T? That doesn't work. Then you go to the second letter. Well, eventually you'll get to the last letter, and you'll see that, if I change this T to an A, that'll work. I'm not sure that's as efficient as trying to compare it a string at a time, but anyway, we'll load the queue with this to start with, and then going through the bank, is there anything that is just one letter different from what we just dequeued? And in that case, there is. This is one letter different. It's just the last letter that changed. What about this one? A, C, C, G, C, G, C, T, A. No, that has two letters different. How about this one? A, and then it ends in an A. No, that doesn't work. All right, so the next thing is we count that as one move. We've cleared one level, and we put this in the queue, dequeue it, and then we say, is there anything left in the bank that is one letter different from this? Let's see, A, C, C, G, C, T, A. Yes, actually this is, so that would go in the queue. And what about this one? A, C, G, G, G. That's also one letter different. That also goes in the queue. We take this off the queue. And now we are looking for anything that is one letter different. Now we can't look at this because we have already visited that. We're also going to keep track of things that we visit so that we don't visit them more than once. A, C, G, you know, that actually, no, it's not one letter different anyway. What about this one? A, is it one letter different from this one? A, C, G, G, T, A. Yes, it is. Okay. And that is the gene that we're looking for. So that took 2 mutations. All right, so that's the basic idea. Let's go ahead and try an implementation. All right, so to do a breadth first search, we're going to need a queue. This will be a queue of strings. We'll call it queue, and that'll be a new array deck. All right, and the first thing we do is put the start gene in the queue. That gets things rolling. All right. Yeah. So typically in a breadth first search, we want to keep track of, and you can think of this as a graph, but we want to keep track of nodes that we've already visited so that we don't duplicate our efforts. So let's do a set of strings. We'll call it visited, and that is a new hash set. All right. We're going to add gene strings to the visited set as we visit them. I mean, another way of doing it is you could just put all of the strings in the bank in the set to begin with, and then take the gene strings out of the set as you visit them. But I prefer this way. Visited, we are also going to add the start gene because we have used it already. All right, we need a counter for how many mutations do we need to make, and now we can go into the while loop. So while not queue is empty for that was weird. Hang on. While, why does it go there? That's strange. I don't know, something's a little bit off. Okay, for int I equals q dot size. Okay, yeah, I made this mistake in a previous problem. I'll talk about it in a second. I greater than 0, and I will decrement I. This is not the same as saying for int I equals 0, I is less than q size, because the q size changes. So we can't use it as a termination condition. It's not a constant. We will be adding things to the queue, taking things out of the queue. So you got to start with the queue size, and then stop when the queue gets down to 0. So let's say string gene equals q dot poll. We'll dequeue the first gene string, and we'll check. This is really a lot like the last problem that we did, which I can't remember. What was the last one? Shoot. Well, anyway, if the gene equals end gene, we're done. Okay. The gene equals end gene, then we can return the depth. All right. If it doesn't equal the gene string, then we're going to go through the gene bank and look for any strings that could be the next string, meaning that they only differ by one letter. Let's do some kind of count. I guess another way to do this, well, let me type a little bit more here and I'll tell you what I was going to say. Yeah, no. For int j equals 0, j is less than 8, which is the length of the gene strings, and c is greater than 0. So what we're trying to do is and j plus plus. What we're trying to do is find strings that only differ in one letter. So yeah, and we're going to decrement here. Start at 2 and decrement. If it gets to 0, that's too much. That means 2 letters are different, or 2 genes. That's too much. I mean, another way to do it, you could say int c equals 0, and then initialize it to 0, and then check that c is less than 2. I'd classify that as like programmer preference. All right. If c is greater than 0, that means it should mean that c is 1, and that we found a gene string that only mutates by one gene, and not visited contains, meaning we haven't seen this before. Next, we will do q dot offer next, and we'll also put next into the visited set. Okay. Yeah, see, this is a little bit off. Really, it should be here. Okay. Is this something looks off here to me. as far as the number of brackets. I'm going to pause this for a second and make sure I am where I want to be. Okay, now I see where I messed it up here. So we are comparing strings letter by letter. We don't want to decrement C unless the gene, okay, yeah, gene is what we pulled off the Q. If gene char at J is not equal to next dot char at J, then decrement. Okay, and really all of this if should be in the for loop. I don't want to go that far with it, but that should be in the for loop. All right. For each string, yes. Okay. For each string, compare if there is a letter different, decrement C. If C gets to 0, it's not going to work. If C does not get to 0, then we've got a string that we can use. It only differs in one gene. So, all right, if. And that is, what does that line up with? With the 4. Yes, perfect. All right. So that's one time through the Q. And so we'll increment depth, and then we'll go again, take the next element off the Q. If we get all the way out of that while loop and we have not returned a correct answer, then that means we can't do it, and we'll return -1. All right. Let's see. All right, I'm gonna try to run that. Int I, oh, no semicolon, line 13. 13, I greater than 0. All right, try that. Okay, basic cases pass. And submit. Accepted. Whoa, ran pretty fast. Okay, later. What is the runtime complexity of this? Think about that. So you've got N is the N is the length of the gene sequence, which would be 8. M is the length of the gene bank. So it's N times N, probably N times M times C, which is the, well, yeah, C, which would be the size of the character set. In this case, it's 4. I'm interested in what they would say is the complexity of this. Something like C times M times N. They're just going to go N times M. Okay, N times M. That's the length of the gene string and the size of the gene bank. But it still would be more, wouldn't it, if we had more than 4 character possibilities? I don't know. Maybe not. Okay, so that is minimum genetic mutation. What is that one I was trying to think of from last time? And this is the whole list here. We are currently on binary search tree, no. Graph general, no. Graph BFS, yeah. Oh, snakes and ladders, yeah. It's very much like snakes and ladders. Anyway, that is minimum genetic mutation. Hope you enjoyed it. Feel free to like, subscribe, comment, and see you next time.